Here's a curious thing. Be a number, a whole number, say 192. Take that number, reverse its digits, then add the two together and you get 483. Okay, not spectacular, I agree, but if you repeat this process a few more times, you eventually reach the number 6996, which is a palindrome, of course. How about the next number, 193? This takes longer, but after 8 steps you reach 2332, which is another palindrome. A self-descriptive one, actually. 2 2s and 3 3s, which I think is rather nice. 194 and 195 also produce palindromes after a few steps, and this of course raises a question. Do all numbers treated this way eventually reach a palindrome? Well, no one knows for sure, but apparently not. The very next number, 196, has been studied for decades and has been taken to millions of steps and billions of digits, but to date no one has ever found a palindrome. Numbers that never reach a palindrome are called Lychrel numbers, and strangely enough, no one really knows for sure whether any exist. Just because no one has found a palindrome for 196 doesn't mean to say that one doesn't really exist. Who knows, a palindrome may appear in the next few steps. Anyway, this channel is all about Pandigital numbers, of course, so what happens when you apply the so-called 196 process to them? Well, some produce palindromes quite quickly. In fact, I found the first 5 and the last 5 zeroless Pandigital numbers all end in a palindrome after only a few steps. Others take a bit longer though. This number is one of 32 that takes 76 steps, which to the best of my knowledge is the longest sequence. A quick search shows that about 60% of Pandigital numbers do end in a palindrome, and the other 40% seem to go on forever. The smallest is this one. No palindrome after 1,000 steps, but again, who knows, a palindrome may appear in the next 1,000. There's just no way to know without looking. Multiplication is another way to turn a Pandigital number into a palindrome. For example, if you multiply this Pandigital number by 99, the result you get is this palindrome. I'll call multipliers like this pan-power factors for the want of a better name, and I found the smallest pan-power factors for the first 5 and the last 5 zeroless Pandigital numbers fairly easy. So, this of course made me wonder whether a pan-power factor exists for all zeroless Pandigital numbers. Only about 360,000 numbers to check, so it didn't take too long, or at least so I thought anyway. Well, after a lot of computation, I found pan-power factors for all except about 1,000. But even for those, I'm pretty sure I'll find one eventually. I'll spare the details. After all, once you've seen one, you've seen them all. But here's some of the highlights. This is the smallest palindrome you can make, and I'm still looking for the largest. This pan-power is the largest prime number I've found so far. This pan-power is itself a palindrome, the largest I know of, and here's a few with curious digital patterns. Palindrome is made up from just 2 distinct digits. So what about the other Pandigital numbers, those that contain all 10 digits? Are there pan-powers for those too? Well, checking through all 3 million Pandigital numbers is a bit of a stretch even for me, but there are results of course. For example, I found pan-powers for all of the 87 Pandigital squares, including this one. It's a palindrome, which when squared equals a Pandigital number, which when multiplied by this pan-power equals this palindrome. There's another result similar to this, so as a challenge, see if you can find it. There are in fact many pan-powers which are themselves Pandigital. This palindrome is a product of 2 Pandigital numbers in 2 different ways, and each half of this palindrome is itself Pandigital. There's even pan-powers that are the product of 2 Pandigital numbers. So, are there pan-powers for every Pandigital number? Well, I think the answer to that is probably yes. Well, unless the Pandigital number ends in a 0, of course. In fact, I suspect that every Pandigital number is actually the factor of an infinite number of palindromes. There are several like this one, for instance. that are clearly the part of an infinite series. Most others are not quite so straightforward as this, but I easily found 12 pan-pals for the first zeroless pandigital number, and I'm sure you'll find hundreds more if you look. Anyway, what do you think? Pandigital numbers can also equal the product of palindromes, and many can be expressed as a product of palindromes in several ways. Others have curious digital patterns. Possibilities are endless. I'll finish off though with this circle I constructed some years ago based on palindromes with 5 digits. If you look carefully, you'll see that the product of any two adjacent palindromes equals a 10-digit pandigital number in the outer circle. There's several other circles like this, but this is the largest one I ever found. And with that, I'll sign off till next time. But as always, I'll end with a solution to the puzzles I posted in my last video. Did you get the same answers as me, or did you do any better? If you did, then please let me know. Until next time, cheerio.